Hello, this is Team Cade, and we'll be talking about collision avoidance in dynamic environments. Autonomous navigation through unknown environments is a difficult task, especially when dealing with dynamic obstacles. We aim to explore this problem in our project. Here are our learning objectives. None of us have previous experience with Unity or C#, and so we had to learn how to code in C# and simulate environments in Unity. We learned various algorithms that have been documented in literature about collision avoidance, especially within the velocity obstacle school of thought. We were able to collect some data from our experiments and compare various methods. For our deliverables, we've set a baseline of completing a toy problem, which means the robotic world would comprise of just simple shapes, making the problem slightly easier to solve. For our stretch goal, we'll be implementing all our algorithms in the ROS Unity environment and demo our robot avoiding human pedestrians and furniture when walking along a corridor.
For our related works, our group already did a thorough analysis and description in our group literature review submission, but essentially our first source of related works were suggested ones by the professor in the project proposal slides from lecture 1. Along with these, our team picked our main focused paper to be a general survey of collision avoidance navigation algorithms, and this led into many different papers which we've categorized under the groups of APF, VO, and ML based. So from the related works, we've reached the following conclusions between the algorithm groups. So for VO, the pros are that it can handle intelligent obstacles, it guarantees convergence, they're not specific to the system, they're simple to create and implement, and they have very smooth trajectories. But the cons are for reciprocal velocity obstacles, you have to assume other obstacles use the same or similar avoidance method. They can deadlock in overly crowded environments and can be difficult to use on holonomic robots. For APFs, the pros are that they're easy to understand and implement, they work for complex environments, they have real-time response and are flexible. But the cons are they can reach a local minima, they have a limited scope, and there's difficulty in tuning their parameters. Finally, for ML, the pros are that they have high adaptability, they are robust, generalized, and efficient. And the cons are that they are susceptible to overfitting, they have a long training time, they have high sensitivity to hyperparameters, and you have to treat them like a black box solution. So our project aims to evaluate the effectiveness of 3 variants of velocity obstacle avoidance algorithms and compare them with the artificial potential field algorithm in dynamic environments. The algorithms will be tested in a simulated environment using a gopher robot navigating through a hospital environment with obstacles of different sizes and speeds. The 3 velocity obstacle avoidance algorithms include acceleration velocity obstacle or AVO, hybrid reciprocal velocity obstacle or HRVO, and machine learning based collision avoidance methods or ML. These algorithms all use different methods to avoid obstacles, and so the algorithm's performances will be evaluated based on their ability to negotiate obstacles, time taken to reach the destination, and the number of collisions that occurred during navigation.
So APF, which stands for artificial potential fields, it is a widely used method for robot path planning that involves defining a potential field that attracts the robot to the goal and repel it from the obstacles. APF is a decentralized control strategy that uses virtual forces to control the motion of each robot. One force is called attractive forces, which are used to move the robot towards the desired formation. The other force is called repulsive forces, which are used to prevent the robot from colliding with each other. The total force acting on each robot is the sum of attractive force and the repulsive forces, and the force will pull the robot to the target and push away from the obstacles.
For VO, it is a first order based collision avoidance that returns the velocities that will result in collision. This includes the size of the obstacle and the speed of the obstacle. Hybrid reciprocal velocity obstacle HRVO is a combination of reciprocal velocity obstacle RVO and VO. RVO assumes that other robots will use the same method to avoid it. Combining RVO and VO can be used to create a passing side preference. Acceleration velocity obstacle AVO takes RVO and adds acceleration constraints to avoid overcompensating and allow it to travel at safer velocities.
Machine learning enables robots to learn and improve from experience without being explicitly programmed. For this project, we'll be making use of proximal policy optimization to train our agent. ML-based approaches to mobile obstacle avoidance have the potential to improve efficiency and adaptability of robotic navigation in complex environments simply because we don't have to explicitly do any programming.
Unity is the tool that we use to accomplish this project. We run all the scripts and tests under a hospital environment. We implement the algorithms into the Gopher robot object and set up male nurses as obstacles, and everything was coded in C#. We thought we could use ROS at beginning. It was no longer needed as we work on this project. The experiment involving Unity and the hospital scenario, we explored the performance of our proposed algorithm in collision avoidance using different scenarios and nurse configurations. Firstly, we used scenario. We had two scenarios with different locations. In the first scenario, we will have one static nurse and one male nurse with set trajectory. In the second scenario, we will have two dynamic nurses and one static nurse. For each scenario, Gopher robot had the same start point and end point while we tested with each algorithm as well. To evaluate the performance of our algorithm, we tracked out 4 metrics, which are as follows: the task completion time, the clearance with respect to the obstacles, the length of traversed paths, number of collisions.
So how the general implementation of our algorithms is as follows. We first give a control script the targeted position that the gopher needs to reach. Then this target is sent to the navigation script, which will generate a global path plan to follow. With the navigation script, the command for wheel velocities are sent to the gopher robot to follow the given waypoints. How the gopher avoids obstacles while moving is from the algorithm agent script. The algorithm agent script computes the preferred velocity needed to reach the goal as well as avoid obstacles. This preferred velocity is calculated using each of our desired collision avoidance methods. The algorithm agent will pull the data needs from other scripts, such as the in-range sensor, which provides obstacle position and speed data within the given range.
APF implementation was relatively easy comparing with other algorithms. The APF agent sends desired velocity to the navigation script by calculating the repulsive and attractive forces. The attractive forces guide the robot towards the target, and the repulsive forces keep the robot away from obstacles. The algorithms use the potential fields functions to calculate the forces exerted on the robot by taking into account the distance between the robot and the target or obstacle. After the simulation with APF algorithm, we collected the CSV file for analyze purpose. The plot showed the trajectory of the robot from the start point to the end point. The other plot was the distance from obstacles versus time, which maintained at least 0.2 meters between obstacle and the robot for both scenarios. Based on this result, APF was able to handle complex setup, but it would take a lot more time as the environment gets more complex.
So the HRVO agent finds the preferred velocity as follows. First, data about each obstacle is obtained from the in-range sensor script. The data needed to create velocity obstacles are relative position, velocity, and each obstacle size. By combining this data, the RVO and VO are created for each obstacle and then combined again into the HRVO, as described in the paper on HRVO. And the script then uses all the HRVOs of each obstacle and selects a velocity outside of them. And this velocity has a slight weight towards the goal, so it guides the robot towards the target position. So as seen from the video, the robot was able to reach its goal while avoiding obstacles. here are some data about those runs, but in general, the robot maintained a distance at least 10 centimeters away from the obstacles, and the times and distances listed here are later compared against the other algorithms, which will be shown later. And we can also see the path the robot took per scene.
The ABO agent takes in data from the range sensor to obtain the relative position, velocity, and the size of any nearby obstacles in order to calculate their RBOs. Then it constrains the accelerations calculated by RBO. Then it picks a preferred velocity, aiming towards the goal while remaining outside the RBO. The ABO agent was able to reach its goal and never collide with any obstacles. It was able to travel relatively quickly, even with constraints on the acceleration, and the agent was never within 10 centimeters of an obstacle, with it taking slightly longer on the second scene, but also traveling a shorter distance.
So to familiarize myself with Unity's ML setup, I decided to implement a toy problem. In this world, both path planning and obstacle avoidance are handled by the AI. For this, we need to feed the model a lot of data, and my computer would often crash during simulations. If I had access to GPUs, perhaps we could have explored the problem of combining path planning and obstacle avoidance. But since we ran into this issue, we focused on just the obstacle avoidance aspect for ML. When creating a machine learning agent, the most important functions that need to be implemented are for collecting observations and taking actions. In collect observations, we feed the agent information about its position and velocity, the goal's position and relative position, other agents' positions and velocity, as well as a laser scan to provide general awareness of the robot's surroundings. Based off of these observations, we can assign rewards to the agent for being in a certain state. In this case, I penalize the agent for straying from the goal, taking too much time, and also colliding with obstacles, while rewarding the agent for moving closer to the goal and facing the goal direction. In on actions received, we obtain an output from our neural network and take action based off of this. In the event that the agent collides with an obstacle, the episode ends and the agent is also penalized. During this exploratory phase is where I discovered different techniques for quantizing straying, such as changes in distance to goal, and a change in heading to the goal. I also discovered that an AI agent can be guided by a heuristic, so I experimented here and implemented two different heuristics, one purely based off the direction of the goal, and one based off the artificial potential field algorithm, and these both showed very promising results. So to simplify the problem and make it more realistic, the only information I provided to the agent in the hospital environment is a laser scan of its environment. The reason being that unless we have a camera with object detection, we can't really classify humans versus stationary objects on a simple robot. From my observations, the robot navigates quite aggressively and exploits the fact that the human will avoid it. I also noticed significant jerking in the motion, and this can be undesirable if the robot is carrying medical supplies. I added a negative reward for changes in angular heading, and this improved performance, but ultimately to provide near perfect results, the ML strategy will require a lot of training and fine-tuning of the reward functions and the hyperparameters used in creating the model. As seen from the graphs, our ML agent stayed between 0.4 and 1.5 meters away from obstacles and successfully completed the simulation without any collisions.
For the first scenario, the distances traveled were all within 0.4 meters of each other and had no collisions. As you can see from our first chart, APF was much faster than the others, completing the scenario in only 17.2 seconds, while the others took around 36 to 40 seconds. For a second scenario, the distances traveled were varied more, with the shortest being AVO at around 15.6 meters and the longest being APF at around 21.9 meters. APF also collided with the wall once, and ML almost doing the same thing, while AVO stayed farther away from obstacles overall. Once again, the times were mostly similar to each other, ranging around 36 to 41 seconds, with the exception of AVO, which took around 56.4 seconds. We also have charts of all the paths here, where green is the start position and red is the goal position. For scenes 1 and 2, AVO and HRVO had very smooth paths with barely any changes, barely any noise, maintained a very smooth pattern. ML had paths similar to AVO and HRVO, except towards the beginning of scene 2, but was not quite as smooth. And APF had more curved paths that occasionally looped around and were not as smooth as the rest. For the conclusion, HRVO was consistent for both complex and non-complex scenarios and avoided collisions well. AVO is the best at maintaining distance from obstacles, but was slow in complex environments. APF was very fast in simple environments, but can collide with obstacles in complex ones. ML was consistent for both complex and non-complex scenarios, but could potentially improve over use. Although it doesn't collide with obstacles frequently, but it gets very close. So here's our team members. The literature review was split into 3 papers per person, and the final report was split by their variant of the search of the method. Thank you. If you guys have any questions, please ask.